Implementing deep learning models with TensorFlow in PyTorch. Implementing deep learning models using TensorFlow in PyTorch is a fundamental skill in today's AI-driven world. These frameworks simplify the complex process of building intelligent systems, allowing developers to focus more on solving real-world problems rather than dealing with low-level mathematical computations. Whether you are working on image recognition, natural language processing, or recommendation systems, these tools provide the foundation for creating powerful and scalable models. To begin with, it is important to understand what makes these frameworks so popular. TensorFlow, developed by Google Brain, is widely known for its robustness and scalability. It is designed to handle large-scale machine learning applications and is often used in production environments. TensorFlow provides a complete ecosystem, including tools for deploying models on mobile devices, browser, and cloud platforms. This makes it an ideal choice for projects that need to move from experimentation to real-world deployment efficiently. In contrast, PyTorch, developed by Facebook AI Research, is known for its flexibility and ease of use. It uses a dynamic computation graph, which allows developers to modify models during runtime. This feature is especially useful during research and experimentation, where frequent changes are required. PyTorch feels more intuitive and closer to standard Python programming, making it a favorite among beginners and researchers alike. Even though TensorFlow and PyTorch differ in design philosophy, the process of implementing deep learning models in both frameworks follows a similar structure. It all starts with clearly defining the problem. Understanding the problem is crucial because it determines everything that follows, including the type of model you choose, the kind of data you need, and how you will evaluate the results. For example, solving an image classification problem requires a different approach compared to building a chatbot or forecasting stock prices. Once the problem is defined, the next step is data preparation. Data is the backbone of any deep learning system. Without high-quality data, even the most advanced models cannot perform well. This stage involves collecting relevant data, cleaning it to remove errors or inconsistencies, and transforming it into a format suitable for training. For instance, images may need to be resized and normalized, while text data may require tokenization and encoding. Both TensorFlow and PyTorch offer efficient tools for handling data. TensorFlow provides the TF data API, which allows developers to create highly optimized data pipelines. PyTorch uses dataset and data loader classes, which make it easy to load, batch, and shuffle data during training. These tools ensure that the model receives data efficiently, which is critical for performance. After preparing the data, the next step is building the model. This is where you define the structure of your neural network. In TensorFlow, the Keras API provides a simple and user-friendly way to build models by stacking layers. You can quickly create models using a sequential approach or design more complex architectures using the functional API. In PyTorch, model building involves defining a class and specifying how data flows through the network. This approach gives developers more control and flexibility, allowing them to experiment with custom architectures. Although it may require slightly more code, it provides a deeper understanding of how the model works internally. Once the model is built, training begins. Training is the process through which the model learns patterns from data. It involves passing data through the network, calculating errors using a loss function, and updating the model's parameters using optimization algorithms like ADAM or stochastic gradient descent. Over multiple iterations, the model gradually improves its predictions. TensorFlow simplifies training by providing high-level functions that handle the training loop automatically. On the other hand, PyTorch requires developers to write the training loop manually. While this approach demands more effort, it offers greater flexibility and transparency, making it easier to customize the training process. After training, evaluating the model is essential. Evaluation helps determine how well the model performs on unseen data. Metrics such as accuracy, precision, and recall are commonly used to measure performance. Visualization tools can also be used to analyze results and identify potential issues like overfitting or underfitting. Once the model performs satisfactorily, the next step is deployment. Deployment involves integrating the trained model into real-world applications. This could include serving the model on a web server, running it on mobile devices, or deploying it in cloud environments for real-time predictions. TensorFlow provides tools like TensorFlow Serving and TensorFlow Lite, while PyTorch offers Torch Serve and support for exporting models to other formats. As you progress further, advanced techniques can significantly enhance model performance. One of the most powerful techniques is transfer learning. Instead of training a model from scratch, you can use a pre-trained model and adapt it to your specific task. This approach reduces training time and often yields better results, especially when working with limited data. Another important technique is data augmentation. By applying transformations such as rotation, flipping, or scaling, you can artificially increase the size of your dataset. This helps the model generalize better and reduces the risk of overfitting. Custom architectures allow you to tailor models to specific problems. By combining different types of layers or integrating attention mechanisms, you can create more efficient and accurate models. Both TensorFlow and PyTorch provide the flexibility needed to experiment with such designs. Optimization plays a crucial role in deep learning. Choosing the right optimizer, adjusting the learning rate, and applying regularization techniques like dropout and batch normalization can significantly improve performance. Learning rate scheduling, where the learning rate changes during training, is another effective strategy for achieving better results. Handling large datasets efficiently is also important. Techniques like batching, caching, and prefetching help speed up training. Both frameworks support distributed training, allowing models to be trained across multiple GPUs or machines, which is especially useful for large-scale applications. Monitoring and debugging are essential parts of the development process. Tools like TensorBoard help visualize training progress, track performance metrics, and identify issues early. These insights make it easier to refine models and improve their performance. In real-world scenarios, implementing deep learning models requires a structured workflow. It involves defining clear objectives, managing data effectively, tracking experiments, and continuously improving models through iteration. Deep learning is rarely perfect on the first attempt, so experimentation and refinement are key to success. Deployment also introduces new challenges. Models must be optimized for performance, especially when running on devices with limited resources. Techniques like quantization and pruning help reduce model size and improve efficiency. Additionally, monitoring models in production is crucial to ensure they continue to perform well over time. Collaboration is another important aspect, especially in large projects. Organizing code, maintaining version control, and documenting processes ensure that models are reproducible and easy to maintain. Tools like Git and shared repositories facilitate teamwork and streamline development. In conclusion, TensorFlow and PyTorch have transformed the way deep learning models are built and deployed. TensorFlow is known for its scalability and production capabilities, while PyTorch excels in flexibility and ease of use. Both frameworks provide powerful tools that enable developers to create intelligent systems capable of solving complex problems. By following a structured approach that includes problem definition, data preparation, model building, training, evaluation, and deployment, you can successfully implement deep learning models for a wide range of applications. With continuous practice and experimentation, these frameworks can help you unlock the full potential of artificial intelligence and build solutions that make a real impact in the world.